welcome everybody. My name is Thomas Zemen. I'm working as principal scientist here in Austria in the Austrian Institute of Technology. And I will present two results from projects that have been done nationally on active reconfigurable intelligent surfaces for the millimeter wave band. My presentation will be a little bit more different than what we saw before, since one project has ended, so we really have some tangible results to talk about already. The AIT is a research and technology organization with 1,400 employees. It's the largest applied research organization in Austria. And I'm leading there the Reliable Wireless Communication Group, where we have a strong focus on green 6G technologies, mainly on the physical layer. And we have built up multiple proof of concepts to really investigate this with empirical data and do some research on the various challenges that remain. This is a distributed massive MIMO system. We work also on multiband for vehicles and on intelligent surfaces, and this is what I will show today. So I think in general, the idea of reconfigurable intelligent surface is already quite well known, especially in the millimeter wave band. You can easily block the line of sight between the base station and user equipment, because you need the directivity of the base station to achieve a good SNR. So in this case, when you want to operate a reliable link in an indoor automation control task, for example, this kind of situation is not very favorable. So in this case, we place a RIS on the wall or the ceiling of an environment so that the base station can simply circumvent the blocking object. The RIS has to adjust its angle of reflection, and even more can even focus on the position of the user equipment. And in this talk, I will discuss with you a first proof of concept that we have realized for the millimeter wave band. So we have considered the quantization of the RIS state and what this means for the actual result. And I will show you our design for an active RIS element design that uses a polarization transform. Then we have looked into the control of the RIS elements when we have a general set of hardware capabilities in the reflection coefficients. And then finally, I show you empirical measurement results that we compare to our numerical simulation. All this is then put into the context of an automation use case where we actually have built a lab to control an equipment in an XY plane, where we can then explore the control algorithm of the RIS to reach this user equipment. And finally, I'll show you some latest result on our digital twin for the wireless communication system. It is implemented using a ray tracing technology that can analyze such automation use cases. So the actual RIS is here shown in a very schematic form, introducing some basic maths. Basically, you have a base station and the user equipment. This is shown left and right from this blue wall. The blue wall blocks the line of sight. The RIS is here magnified to make it more visible. And basically, we use the models that have been proposed by Tang in 2021 that you see on this equation. Basically, we describe the received power based on the transmit power and the configuration of the RIS elements. Everything has a certain antenna pattern. And in the end, it is basically a ray tracing solution of this kind of communication scenario. With this setting, it becomes also clear that when you want to achieve the best performance of the RIS, so the highest SNR, you have a closed form solution for the actual configuration of the reflection coefficient. This is determined here with gamma m. And this describes in phase and amplitude the configuration of each element. And you can solve this. You find the Xi of m that describes the phase that you would adjust at each RIS element to reach a focusing at a certain point in space. Now, when you realize with the hardware, you have to deal with the limitations. And basically, you can quantize this phase state in a set of finite intervals, namely Q. And we have then looked into what happens when we have a small number of intervals. How much power would we lose compared to the ideal state? And you see this in this graph. So with 2 intervals, we lose around 4 dB, and then the actual loss decays. But in the end, it turned out that we all were we didn't expect that with 2 states only, you lose only 4 dB. So this is actually what we chose to do our first prototype. because this allows us to realize a hardware with limited constraints on the space. And with this kind of setting, we could do a first evaluation of the expected beamforming pattern using this hexagonal structure that you saw previously. We had 37 elements of this RIS, and we chose two reflection coefficients for these two states, namely with 90 and 270 degrees. So obviously the phase difference are 180 degrees. And in this power pattern, azimuth and elevation on the two axes, and you see the incoming direction and the outgoing direction where we could achieve the focusing as we intended it, and the specular refraction that would be the normal way of reflecting a wave could be suppressed. Now, when we do the RIS design, you all know that millimeter wave and even higher frequencies incur a certain higher path loss. So we have been interested to amplify the received signal at each antenna element individually. So this RIS patch antenna element has a vertical and a horizontal port. We take the signal from the vertical port, feed it over a matching network to a field effective transistor, and then the amplified signal again over a matching network to the horizontal port. With this, we achieve an isolation between the two signals, and we can amplify the actual signal. So both voltages at this field effect transistor, the gate and the drain voltage, we can adjust with 1 bit. And with this, we can operate this element in a reflective and in an active mode. In reflective mode, basically, we use a gate voltage to change the phase difference. And in active mode, we can switch on the amplifier or we can switch it off. And this, in the end, results in two reflection coefficient alphabets that you see here on the right side of the slide. So in the reflective mode, we had to deal with some limitations of this initial hardware design. So we could achieve a phase difference of 0 and 67 degrees. When we have realized that we have to deal with this, we also needed a new way how to compute the actual reflection coefficient alphabet, the reflection coefficient settings of our RIS. And the closed form solution that I showed you initially doesn't work. So we actually need now to do a joint maximization of all the RIS element states. This gives us, in our case, 2 to the power of 37 solutions. And this is clearly a too large search space to do exhaustive search. So what we actually did is we implemented a simplified Monte Carlo search, simply choosing the elements randomly and then trying out which RIS state gives an increase in the received power. And it turned out that this works quite reliably and converges fast enough for our actual experiment. Now, when we did this together with the colleagues at Siemens, we built an anechoic chamber setup with a quite sophisticated positioner system. And you see this on the left side. On the right side, you see first the numerical simulations in reflective mode and active mode. And on the right side, you see the empirical measurements. So what we see here is that we have a limited set of reflection coefficients that you can choose from, and we don't have 180-degree phase difference. This means we can achieve an outgoing direction focusing as we intended, but we also have a specular reflection that is visible here on this slide. And in the empirical measurement result, we see that we have achieved indeed the outgoing direction that we wanted, but we also see signals in the specular reflection. We have obviously disturbances from measurement noise in this example. When we now go to the active mode, we see here the same picture, but now with, of course, increased signal power, and the same thing then also with our empirical measurements. So based on this measurement and data, we could design an improved reflective surface. Now we have 127 elements, and you see here on the left side the PCB that was built by Siemens. And on the right side, you see our RIS lab at AIT that we have also built in the last years to actually investigate certain use case scenarios. And this improved RIS has a better matching network, so we can really achieve a reflection coefficient alphabet now where the phase difference is exactly 180 degrees, as it is what we want to have. And we have a certain amplifying set, so we can improve between reflective and amplification mode by a gain of 6 dB. And now we are interested in the actual use case. So we are interested in this automation control use case where you have a mobile UE that moves around, in our case, on an XY grid, on the XY table. And with this, we have investigated what we would receive and which kind of beam pattern do we need to deal with. And again, you see here our numerical simulation of this scenario that you see here on the left side. And on the right side, you see the measurement results. So basically here we have been interested to see, we have several points where we want to move the user equipment to, and then we need to update the reflection coefficients of the reflective surface. And when you see now the actual shape of this focusing pattern, it's actually elliptic. So when we move in azimuthal direction from P2 to P1, we have to update more often than when we move in radial direction. And this is an important information for a practical implementation of a control algorithm. Finally, when you really have an industrial environment, you have non and anechoic situation. You have strong reflectors from metallic objects and other objects, and therefore you really need a digital twin of the communication system for such reflective scenarios. So at AIT we have a ray tracer implemented on a GPU, and this we have now extended to include a reflective surface. How did we do this? A reflective surface is basically emitting a signal or reflecting a signal, so we can treat it using the image method. And with this, we can actually configure and figure out which reflective paths are at all available from the RIS. You saw previously that the RIS indeed focuses on the point, but has also side lobes, and this will show up due to reflections. And in the small scale fading pattern that we can now evaluate, you see here our latest result. Left, you see the measurement from an anechoic situation. Then you see here the simulation with a ray tracer, assuming no reflection. So it gives us exactly a very nice match with our measurements as well. But now we have switched on the reflections to be expected. And then you see a small scale fading pattern from these reflections. And it turns out that this numerical twin is really crucial when you want to design the RIS control algorithm in such an environment. Okay, this brings me to the end of my presentation on our active RIS that we have realized as a proof of concept for the millimetre-wave frequency band. It actually uses a polarization transform to increase the isolation between the impinging and reflected wave, and increases the outgoing signal compared to a simple reflective RIS design. We used a very coarse quantization of the RIS state, namely only 2 states, but it turned out that this is already sufficient for many applications, and the SNR loss is quite minor. When you go to a real use case, for example, in an industrial setting, then it is extremely helpful to have a digital twin, in our case based on a ray tracer, so that you can have a focused design of your control algorithms. So currently we think that the RIS is a promising technology for such reliable indoor millimetre wave communication links. Thank you for your attention.